So we are finally in Unit 4, and Unit 4 is all about the periodic table and periodicity. Periodicity just means there is a periodic pattern in the way that the chemical and physical properties of these elements occur when I look at them on the periodic table. So this is a wonderful extension from Unit 3. I think Unit 3 and Unit 4 go together really well, so a lot of this is probably going to feel nice, warm, and cozy. So let's see. So the historical development of the periodic table. During the 19th century, chemists began to categorize the elements according to similarities in their physical and chemical properties. The result of these studies was our modern periodic table. So there are two scientists we need to know that were super duper important in the discovery and arrangement of the periodic table. Our first guy was Dmitry Mendeleev. 1869. He was a Russian chemist who published the very first periodic table. Now, at that time, there were only 63 known elements. He organized his table by increasing atomic mass and by similar properties. So down here at the bottom, you see some pictures of his first sketches of his periodic table. Okay, some of the element symbols you can actually see. I see a hydrogen, I see a lithium, I see a sodium. He also has a number after the dash. Those were his masses of those elements, as they knew the ones for the elements at that time, at least that they knew of. So here's the wonderfulness of Mendeleev's periodic table. He was not the first person to grab these elements and be like, oh, cool, all y'all over here in this group, y'all all react with water. Y'all are the same. Or, oh, you guys over here, y'all are all solids. Y'all are kind of the same. Oh, you guys over here, you react with this group, so y'all are the same. Y'all don't react at all. Y'all are the same. People had done that before. But what Mendeleev realized, he's like, hey, if I kind of organize them by properties and by mass, there's going to be some holes in here. Because there should be something in there that maybe we have not yet discovered that has a mass of that unidentified element. So he said to keep the elements with the same properties in the same groups, those spaces had to be left. So Mendeleev hypothesized that these spaces represented undiscovered elements. And a search for these elements now resulted in the 118 known elements today. So we call him the father of the periodic table for creating this first organization that not only put everything in perfect little categories, but allowed for these holes of undiscovered stuff to be identified later. So we're going to watch this really cool video about why Mendeleev's periodic table was so fabulous.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka-aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
I just think that is so cool, you guys. So not only was he like, yeah, there's got to be an element here in these blank spots, he was like, yeah, there's an element here in these blank spots, and it's going to look like this. It's going to be like this. It's going to react like this. And for him to do that and be pretty much right on, I think is just one of the most cool things. If that didn't get you excited about science, I don't know what does. So let's see what's next. So after Mendeleev was our second scientist that we know that is important in creating our periodic table as we know it today. So that is Henry Moseley. So in 1913, he was an English physicist who primarily worked with X-rays. And with the result of the discovery of the concept of nuclear charge, which eventually we learned were protons inside of that nucleus, he decided to rearrange the elements in order of increasing atomic number. So he organized them by the number of protons, which we know is the atomic number, and that created a little bit more of a structure to the periodic table today. So we call Henry Moseley the father of the modern periodic table. And at the time that he did this, there were only 92 elements discovered, more than what Mendeleev had to work with, but still only 92. So he's credited with the discovery of the modern periodic table. And here's his periodic table. It looks a little bit different than the ones that we have today on our papers, but he did a great job back then in 1913. Okay, so this brings us to the heart of Unit 4, the periodic law. That states when elements are arranged in order of increasing atomic number, meaning counting protons 1, 2, 3, 4, 5, 6, etc., there's actually a periodic pattern in their physical and chemical properties. So a pattern is when you see something repeat over and over and over again. So basically what the periodic law says is if I move left to right, like I'm reading a book down my periodic table, I'm going to start seeing some repeating patterns within each row. Okay, so this is the periodic law. So let's talk a little bit more in depth about the organization of the periodic table. So elements are listed by atomic number. This is the key to the organization of our periodic table. So our atomic numbers are the big numbers on top of my element symbols. They represent the number of protons. Periods are my horizontal rows of my periodic table. Elements in the same period all have the same number of energy levels. Now we're fresh off of learning just electron configuration, and as we know, every time I enter a new row, you guys were saying like 1s, 2s, 3s, 4s, 5s, etc. And we know that 1, 2, 3, 4, 5, we knew that was a big number in the configuration that did represent the energy level. So each one of these periods, as I cruise on through them, is going to have elements that all have the same number of outer highest energy levels. Our groups, another term for that is a family, the vertical columns in my periodic table. So elements in the same group all have the same number of valence electrons. If you'll remember, valence electrons are the outermost energy levels, S and P electrons only. So they have the same number of valence electrons. And as a result to this, that means they have the same physical and chemical properties. Guys, it is all about the electrons. The reason why all chemical reactions occur is because of the electrons, specifically these valence electrons, okay? Another way, or the reason I think that we call it a family, these groups, is because everybody in my family, we all talk the same, we all look the same, we all sound the same. Similarly to this, elements in the same groups or families, they all act the same, look the same, talk the same, except in chemistry. Okay, so I'm going to bounce on down here, and I thought we could label some things on our little picture that I gave you guys on our notes handout here. So once again, my rows are called my periods. There's period number 1, 2, 3, 4, 5, 6, 7, right? And so these are my period numbers, right? And then over here across the top, I have labels for my group numbers. They're kind of small to see, so I thought we would kind of make them a little bit bigger, especially because on the back of this notes page, we're about to talk about all of these groups. So this is your group number 1 right here. Here's your group 2. Transition metal block, first one is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then hop on to the P block, 13, 14, 15, 16, 17, and 18. So this stuff here, let's see if I can make it not look so sloppy and terrible. These are my group numbers. Okay. So periodic table is arranged by periods, which are my rows, and my groups, which are tops. Everybody in the same period has the same number of highest energy levels, and everybody in the same group has the same number of valence electrons. So going back to our slides, okay. Now the periodic table does have a little staircase that runs right through the middle, and that staircase is important because everything to the left of the staircase is what is known as a metal, except for hydrogen. Hydrogen is a non-metal. He should be over here with the other group, but based on his ability chemically to react with things, he tends to be classified over there anyway. Okay, so metals form cations, which means they form positive ions, and they lose electrons. I feel like y'all have heard me say this a lot. You will hear me say this all year. Cations are positive and they lose electrons. Metals usually tend to be solids. They're also usually good conductors of heat and electricity. That just means they can allow heat or electricity to pass on through them from one side of the sample to another. That's why when you put a metal pan on your stove, it heats up very quickly, right? Metals are also ductile. Ductile is just a fancy term to mean it can be drawn out into a teeny tiny thin wire. And metals are also malleable, which just means you can hammer it down into a thin sheet. My nonmetals are the ones up here to the right and up of this staircase, including hydrogen over there. My nonmetals form anions, which are negative ions, which gain electrons. My nonmetals can be gases, liquids, or even solids, but they are poor conductors of heat and electricity. And my solid nonmetals tend to be quite brittle. Now, all of these terms where we've been talking about like what state of matter these guys are in, their conductivity, how they look, we will expand on this a lot more when we take these metals and nonmetals and look at how they react or how they behave when they are bonding with other things. And we will kind of really unpack this conductivity and state of matter and stuff in that lesson. but I did kind of want to map it out here today. Okay, now we got the metalloids. So the metalloids are along that darkened black line staircase, except for aluminum. Aluminum is a true metal. And metalloids have properties of both metals and nonmetals. And as you could expect, they can conduct electricity and heat sometimes, or only under certain conditions. So we call that semiconductors. Okay, so I'm going to bounce on down. Let's see what I want to do here. So on our thing, on our periodic table, our little teeny tiny one right here, if you want to draw a little line showing that our metals are to the left of the staircase and our nonmetals are to the right of the staircase. And then we have our metalloids, and you don't have to worry about which ones you are grabbing, just making sure that you realize, oh yes, my metalloids are here along the staircase, metalloids. Okay, amazing. So next thing I want to do is I want to do like a little chemistry hunt and search kind of game. So I'm going to get my yellow periodic table, which is a little bit easier to see. I'm going to zoom out quite a bit here. And they're saying, okay, who is the element in group 17, period 4? So we know groups are my vertical columns. So group 17, period 4. So that would be 1, 2, 3, 4. And it looks like I have bromine there. And the next one is, who is the element in group 2? So group 2 is all the way over here. So group 2, but period 3. So here's the first period, second, third. So group 2, period 3 looks like we are magnesium. And the next question says, list all of the metals in group 14. So group 14, group 14, group 14. Here you are right here. All of the metals. Well, we know my metals are going to be to the left of the staircase here, so definitely not carbon. Silicon is a metalloid. Germanium is a metalloid. So all of my metals will be everybody below that. So that would be tin, lead, and fluorovium. And the last question is list the nonmetals in group 15. So group 15 is the group right next door. And they want me to list the nonmetals. So the ones that are going to be over here to the right of the staircase. So obviously I'm going to pick up nitrogen, right? And I'm going to pick up phosphorus. Arsenic is a metalloid. Okay, so let's see how we did. Yep, bromine, magnesium. We got all of the metals. If you'll notice, I put germanium in parentheses because he's a metalloid. So the argument could be made that he is metal-like under certain conditions, which I will give that to you guys. Same thing with arsenic as a non-metal. He can be metal-like in some conditions. All right, let's see what is next, you guys. Okay, specify a metal or a non-metal. I'll give you guys some time to do this if you want to pause the video. Okay, let's see how we did. I'm excited. Yes, sulfur is going to be to the right of the staircase, so a nonmetal. Same thing with chlorine. Sodium is to the left of the staircase, so he is a metal. Iron is to the left of the staircase, metal. Carbon's to the right, a nonmetal. Silver is to the left, a metal. Excellent. You know, when I start repeating myself, that means things are important. When I repeat myself lots and lots of times, it's important for us to like really get that into our heads to where we don't even have to think about what metals and non-metals are. Okay, so now we're going to talk about some of these really, really important groups on the periodic table and what specific properties they have. I mentioned before that another term for a group is a family because everybody in the same family looks alike, talks alike, sounds like, all that stuff. Okay. So our first important group of the periodic table are the alkali metals in group number 1. Let's learn about the alkali metals. Oh my goodness. So group 1, the alkali metals. So that is everybody in group 1 except for hydrogen. We just had a conversation that hydrogen is actually not a metal at all, but he has properties similar to the alkali metals in other ways. But the alkali metals, excluding hydrogen, they are the most reactive metals on the periodic table. And this is because they have only one valence electron. So we mentioned before that everybody in the same group has the same number of valence electrons. We will map that out here in a second. But the alkali metals, they have one valence electron. Well, why does that make them reactive? If I got one valence electron, I'm going to lose it real fast. It's only one of them. So they do. They tend to lose it quickly. And when they lose their valence electrons, that means they are reacting. So they're reacting quite quickly. So as a result, if I'm reacting really, really quickly as an alkali metal, you're almost never found by yourself as a pure element in nature. Specifically, they will explode in water if you put them inside water. There is water vapor in the atmosphere, so if we have pure samples of the alkali metals, they have to be contained in oil without exposure to the air, which is really exciting. So there's an amazing video of exploding the alkali metals with water that I thought we could watch right now.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
Okay, you know, that video I feel like is super old, but you can find a ton of videos of the alkali metals reacting with water on YouTube. But that one I still think is the most captivating one and does the best job at actually showing the difference between the alkali metals and their reactivity in water. And no, we do not have alkali metals at our school currently. I'm hoping that maybe next year we can get some so we can actually drop them in water in person. I think that would be fun. But okay, let's talk about why are they all reacting this way? It is all about that valence electron. If you'll remember, each one of those guys, those alkali metals, are the first guy in that period. And so they will all have an electron configuration of NS1. And then as a result of that, all of the elements in that group have one electron in their outermost energy level. So we would say that they all have 1 valence electron. Now, one thing I want you guys to notice, they showed in the video them dropping lithium and then sodium and then potassium and then rubidium and cesium. And I hope that you were noticing that, hey, things got a little bit more reactive with water as I went down within that group of the alkali metals. So probably they could not get a hold of some francium because maybe it would have been a little bit too dangerous. We're going to kind of unpack why reactivity tends to get more and more and more intense as we go down these groups here in a second for the alkali metals. Or not here in a second. Eventually we'll get there and we'll tie it all together with a nice little present. It'll be nice. Okay, next one, we got group 2 of my periodic table. Group 2 are called the alkaline earth metals. So the alkaline earth metals are also pretty reactive. Not quite as reactive as the alkali metals though. But as a result, since they like to react a lot, they're not usually found as a pure substance in nature, okay? So those are my group 2 elements: beryllium, magnesium, calcium, strontium, barium, and radium. You guys, they usually are found paired up or bonded with something else because they like to react in order to be happy. So my alkali earth metals, they all have an electron configuration of Ns2. So as a result, all elements in this group have 2 electrons in their outermost energy level. So that means they have 2 valence electrons. All right, now we're going over to this collective block. We're going over collectively to the transition metals. This is group 3 through 12. So my transition metals are this middle block. We call this the D block, right? And we don't have specific, just, warm family characteristics here at the transition metals because they have a lot of varied properties. Okay, and the reason why there's a bunch of different properties and stuff with the transition metals is that their electron configurations tend not to be as clear cut as the guys in my S block and my P block are. So as a result, we can kind of only generalize these transition metals as behaving something that is metallic-like. Now on to the F block of the periodic table. These are what is known as my inner transition metals. So the 2 rows that make up the F block are, the first row is the lanthanides, which starts with the element lanthanum. And the second row are the actinides, which starts with the element actimum. Okay? They also have very weird, varied electron configurations, especially since they are bigger elements. Stuff gets a little bit less clear cut there. My lanthanides, a lot of them are used for electronics and in magnets and stuff like that. My actinides, a lot of them tend to be radioactive, so they're used with nuclear energy and atomic bombs and stuff like that, which makes them exciting. Next group. So these next groups, 13, 14, 15, 16, are not a special name for these groups, so I'm not going to spend a lot of time talking about it, especially since they're the groups that have crossing over the staircase, where we do know that we tend to have some metal representatives and some also non-metal representatives. So it's kind of hard for us to characterize these specific groups as being true families, to where they have a cohesive kind of behavior. But my group 14, I'm going to call it the boron family, just so you know that starts with boron and everybody below him. But the main thing that they do have in common is all elements in that group have an electron configuration of Ns2, Np1, because boron's family is one place into the P block. Okay, so as a result of that, if I'm Ms2, Np1, the elements in this group have 3 valence electrons. And this is a picture of gallium from the Mendeleev video. Yes, gallium will absolutely melt in your hand. It is a metal with a very, very low melting point, which is super exciting. Okay, group 14, that is the one that starts with carbon. So we're going to call this the carbon family. The most important thing about group 14 is that they all have the same configuration of Ns2 and then Np2. So 4 valence electrons. So here's a picture of carbon, and yes, carbon is what diamonds are made out of. And we have silicon and lead. So we've got a mixture of metals and non-metals here in group 14, but the configuration for everybody in group 14 is the same. Okay, group 15, this is the group that starts with nitrogen. All elements in this group have an electron configuration of Ns2, Np3, so together that makes 5 valence electrons. Okay, and we got nitrogen, phosphorus, arsenic, antimony, bismuth, and whatever MC is. We do not use MC that much, so he is not super important to me at least. Okay, so now we got group 16. This is the group that starts with oxygen. All elements in this group have an electron configuration of Ns2 and P4 because they are 4 element blocks into that P block. So everybody in this group has 6 valence electrons. All right, now we start getting excited because we got an important group coming up here. We've got group 17. Group 17 is what is known as the halogens. Now, group 17, they are all nonmetals here, okay? We are done with the staircase. We are now in a group that is strictly all nonmetals. Group 17, your halogens are the most reactive nonmetals on the entire periodic table. And this is because they have 7 valence electrons. We know that atoms want to get 8. He is so close to 8 electrons that he tends to gain an electron very, very, very quickly. And as a result of that, they're almost never found as a pure single atom in nature, and instead tend to form salts or other compounds with metals, okay? So our halogens are fluorine, chlorine, bromine, iodine, astatine, and whatever TS is. Now, here's the cool thing. We talked about our Hofbrinkels, right? The ones that always come into many of our diatomic elements are halogens because they desperately need to bond with something, even if it's one of themselves, in order for them to be happy. They are very, very reactive. So the halogens, all elements in this group, have an electron configuration of Ns2, Np5. So 2 plus 5 gives you these 7 valence electrons. That brings us to our final group, the noble gases. This is group 18. And the noble gases are all gases, and they are unreactive. And the reason why they are unreactive is because they have a full valence shell of 8 electrons. And if they have a full valence shell of 8 electrons, they are not trying to get more electrons to make 8. They're also not trying to get rid of electrons to make 8. So they rarely react with other elements. In fact, no compounds with helium or neon have even ever tried to be creative. My noble gases. There's krypton here in the middle. Sulfur over here says, does anybody have any extra electrons? And then magnesium and oxygen. Notice they're holding hands. This is a nice little preview into bonding when we talk about it. The magnesium and oxygen, they're like, oh, he's hardly reacting at all. So our noble gases, all of them have a configuration of Ns2Np6, a fully filled P room or P block. So that 2 plus 6 does give you the 8 full valence electrons. Okay, so it's all about these ding-dang electrons, okay? So let's talk a little bit more in depth about valence electrons and what that means in terms of why you're reactive or why you're not, or what you can do to try to get a full shell of 8. So valence electrons are the ones that are found in the S and P sublevels of the outermost energy level of an atom. So they are the electrons that will be lost, gained, or shared when you form chemical bonds. So the valence electrons are important because that is what is needed or used to do chemistry, okay? Bond formation involves either losing electrons off of the atom, gaining electrons into your atom, or sharing electrons with another atom. That is what all bonding, all chemistry is at its heart. And then no matter the size of the atom, the valence electrons are always just the ones on the outermost, just the ones in the S and P. So on our blank periodic table, which everybody did get today, we are actually going to label some things first. We're going to label valence electrons, and this will probably be the most important thing you ever label on a periodic table because we'll be looking at this over and over and over again. So over here off to the side, we're going to write a little thingy that says VE. Yes? And then we're going to write the numbers representing the valence electrons. Sorry, you guys, I feel like it's super noisy back there. We just got some new guinea pigs in there. Oh my gosh, they're being very loud. This is a very professional video. Anyway, we're going to talk about valence electrons, y'all. So valence electrons, first group, he's got 1 valence electron. And you know what I'm actually going to do, guys? So I'm going to make sure I can see it real good. I'm going to circle that one. So group 1's got 1. Group 2, it's got 2 valence electrons. I skip over this. Remember, transition metals and intertransition metals, things get messy. Like they could have a bunch of different valence electrons. We do not know. So I'm going to move over here to group 13. Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. 16 has 6. 17 has 7. And then 18 has 8. My noble gases with the full 8. So this, oh my gosh, look how nice and important and wonderful this is. I'm very excited about that. So those are our valence electrons by what group you're in that we have now labeled on our periodic table for this unit. So we've been talking about the 8 valence electrons, and that's so important to have 8. So this is known as the octet rule. Hopefully oct makes you think of like 8, like an octagon, which is an 8-sided shape. Octet has to do with these 8 valence electrons. So it says in bonding, atoms will either lose, gain, or share electrons in order to have a full outer energy level. For all elements, except for hydrogen and helium, a full outer energy level will have 8, right? So if I look at my periodic table and I grab the S and the P, if I add those together, that's going to give you 8, okay? Hydrogen, helium, says they only need 2 to fill their outer energy level. Well, hydrogen and helium, they don't even have a p block, right? They're only in the s block. So the 2 electrons that would be required are only going to fill up that 1s sublevel, that 1s room. So oxidation number. I said valence electrons were important. This is probably even more important than valence electrons, but it is a result of the valence electrons. So an oxidation number represents the number of electrons needed to be lost or to be gained in order to complete an atom's octet. It represents the charge of the most common ion that an element will make. Since all elements on the periodic table in the same group have the same number of valence electrons, guess what, you guys? All elements within the group will also have the same oxidation number. Metals tend to lose electrons and have positive oxidation numbers. They tend to form cations. Oh my gosh, this section is so important. I hope y'all are hearing me. I feel like I want to repeat this 1,000 times, but I will not. If you want, you can stop the video, rewind, and let me repeat it 1,000 more times on your own time. But metals lose electrons and have positive oxidation numbers. They form cations. Non-metals tend to gain electrons and have negative oxidation numbers, and they form anions. Ooh, oh my goodness. Oh my goodness. So now we're going to bounce back down. I'm getting excited again. Even though I'm kind of sick today, I'm getting excited. Okay, we're going to write oxidation numbers and how that relates to our valence electrons. First, we're going to write it, and then I'm going to talk, because you know how I like to talk, and I really like to talk about oxidation numbers. So here we go. Oxidation numbers. I'm going to write ox and then the number sign. And so above group number 1 with his 1 valence electron, the oxidation number of that group is going to be a +1. So we're going to write +1. Group 2, oxidation number is going to be a +2. Group 3 is going to be a +3. You guys, these guinea pigs, I'm sorry. I'm going to have to move them to another room next time I make a video because they're being crazy. Okay, group 4 has +4. You're like, I'm so excited. I know exactly where this is going. Oh, no, you do not, because I'm about to go -3 on group 15. And then I'm going to go -2, and then -1, and then 0. This you will commit to memory, knowing what the oxidation number of every single group is. Now let's talk about what this means. So we say that atoms want to gain or lose electrons in order to get to a full valence shell of 8. Let's talk about everybody here in group 1. They've got 1 valence electron, right? So let me ask you this. Would it be easier if you had only 1 valence electron in your outer shell to try to get 7 more from somewhere to make you feel happy for 8? Or would you just want to like kick off that 1 electron, exposing another energy level underneath that would already be full? They're going to do that. So this +1 represents them losing 1 electron to where they can have their full valence shell underneath be 8 and be full. Group 2, he's got 2 valence electrons. Is it easier to grab 6 to complete an 8 on that level, or to get rid of the 2 you have to have 8 on the level below? Yeah, they're going to get rid of the 2. So they tend to form ions with a +2 charge. Skipping on over, these guys over here, they've got 3 valence electrons. It's going to be a lot easier to lose those 3 than it would be to grab 5. Now here we are with the 4 valence electrons. It is kind of equally as easy to gain 4 more to complete your 8 or to get rid of those 4 to unveil 8 underneath. But we typically see that there is a +4 charge here. That is not always true. And in fact, we are probably not going to be dealing very much with ions specifically in group 14. But this is the halfway point to that octet basically, which things do start getting interesting back over here. If I now go to the 5 valence electrons in group 15, 5 valence electrons. Well, hey, now it's easier for me to gain some instead of lose the ones that I have. Because here I'd only have to gain 3, which is fewer than me having to get rid of 5 that I have. So these atoms in group 15 tend to form ions with a -3 charge. So here's where we start seeing our anions. And they make that charge because that just represents how many electrons they need to add to their current number of valence electrons to complete 8. Now group 16, they have 6. They want to grab 2 more. So they have a -2 charge. Group 17, they got 7. They want to grab 1 more. So they have a -1 charge. Group 18, they already have 8. So they ain't got no oxidation number, guys. They don't form ions because they are already satisfied according to the octet rule. Now remember when we talked about our alkali metals being super reactive? Our alkali metals, wow. They were super reactive because it's real easy to get rid of 1 valence electron. It's a little bit harder to get rid of 2 valence electrons. A little bit harder than that to get rid of 3 valence electrons. The less electrons you need to move around either into your atom or out of your atom, the easier it is or the more reactive that element will be. Same thing over here. I remember we pointed out that our halogens are the most reactive nonmetals. Well, that's because they're only dealing with moving 1 electron into their atom as opposed to moving 2 or moving 3, right? So that is where the reactivity is kind of determined by, okay? So that was very exciting. Let's see what is up next. So we have homework. It says you are going to choose 7 different colors. I will allow you to choose 7 different colors of your choosing. Choose 7 different colors of your choosing, and you will be labeling the special groups on your periodic table. The alkali metals, which is our group 1. Alkaline earth metals, which is our group 2. Transition metals, which is the D block. The inner transition metals, which was our F block. The metalloids, which are along the staircase but not aluminum. The halogens, which is group 17. The noble gases, which is group 18. And then you're going to label which side of the staircase is metals and which side is non-metals. So I have my periodic table down here. And you guys do not need to, do exactly what I did, but I chose some colors here. And I did a little key here in the middle where I had room. I'm going to lift this up a skosh so we can see it a little bit better. Yeah. And I keep in mind this is where we wrote together our valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. This is also where we labeled our oxidation number: +1, +2, +3, +4, -3, -2, -1, 0. So then we have our alkali metals that I colored red, not hydrogen. Alkaline earth metals, I colored orange with their 2 valence electrons and a +2 charge. Transition metals, my inner transition metals. Then my metalloids, which I said are along the staircase, but aluminum is not a metalloid technically. And then my halogens are in group 17 with their 7 valence electrons with a -1 charge that they tend to make. And then finally, my noble gases are group 18 with their 8 valence electrons. I drew an arrow saying that these guys are metals and an arrow that says these guys are non-metals. Now, you will notice that there are some parts of the periodic table that do not have any labels on them, and you were like, well, what am I supposed to do? What are these metals called? They are post-transition metals, I've heard it be called. They are other metals. Same thing over here. These are other non-metals. They're just not in a perfect little box where we will study them collectively as a group like our other groups that we've been coloring here today. But this is a little intro to the periodic table. We learned actually a lot here. We got names of all these groups. We related these groups to what that means in terms of their electron configuration. We remembered that our electron configuration helps us determine the number of valence electrons. And then we knew that the number of valence electrons now also determines what the oxidation number of that group is, depending on if that atom is going to either lose electrons or gain electrons in order to satisfy their octet. Now, this is a preview of getting into bonding, because that satisfying of the octet is where all chemistry happens. Very exciting.